Hi, everybody. Now we're going to give the proof of the second of Sylow's three theorems. And this is a fairly deep result, so let's take it slow and see how it goes. So the second Sylow theorem says the following. Suppose you have a finite group, and you take the largest power of p, which divides the order of the group. Then we know by the first theorem that a subgroup of that order always exists, and we call that a Sylow p subgroup of G. So maybe as a little side remark, for example, if G is S4, so that the order of G is 24, then 8 is the highest power of 2 that divides 24, and so a Sylow 2 subgroup would have order 8 of S4. Would have order 8. And what Sylow's first theorem, as I said, we proved, is that you would know there always exists such a subgroup. What Sylow's second theorem says is that if you have two such subgroups, so P1 and P2 are subgroups of maximal prime power order, so they're Sylow p subgroups inside a group G, then you can find an element of the group where if you conjugate the first subgroup, you get the second. So it's not the case that these subgroups are necessarily normal. If the Sylow p subgroup were normal, that would mean that G P1 G inverse was equal to P1. But at least if you have two of them, you can conjugate one into the other. And I should remark, one thing is clear, or at least not too hard to see, namely, if P1 is a Sylow p subgroup, and you conjugate it, this is also a subgroup, and its order is the same, because the map from P1 to G P1 G inverse given by conjugation, let's call it X goes to GX G inverse. This is an isomorphism. And of course, its inverse is Y in the conjugate goes to G inverse XG. So therefore, if you have a group whose order is P to the R and you conjugate it, you get another subgroup whose order is P to the R. So you know that the conjugates of a Sylow p subgroup are Sylow p subgroups, but you don't necessarily know, and that's what we have to prove, that you can always get from one to the other by conjugation. It could be that there's like one group of Sylow p subgroups over here and another group of Sylow p subgroups over here, and the conjugation action preserves those two things as separate orbits, but they don't cross over. But that can't happen. So let's go back to S4 just to have something maybe a little bit more concrete to think about. So as I mentioned before, S4 has 24 elements, and a Sylow 2 subgroup of it has order 8. So what are these subgroups? Well, one way to make a Sylow 2 subgroup, or to find a subgroup of order 8 in S4, is to take the 4-element cyclic subgroup generated by a 4 cycle, like 1, 2, 3, 4, together with a transposition, like 1, 3. And if you take the smallest subgroup which contains these two elements, what you get is a copy of the dihedral group for the square, which we've seen many times and which has 4 elements. And if you think of the symmetries of the square as acting on the vertices labeled 1, 2, 3, 4 in this way, then the cycle 1, 2, 3, 4 is the rotation, and the reflection 1, 3 is what you get if you reflect around this diagonal line, because it fixes 2 and 4 and interchanges 1 and 3. And combining those two things, you get the subgroup of 8 elements, and I've just listed them here. So you have the rotation to the right and to the left, the 180-degree rotation, which takes 1 to 3 and 2 to 4. So this is R squared. This is R cubed. And then these are the 4 reflections corresponding 1, 3, and 2, 4. These are the diagonal reflections, and 1, 4, 2, 3 and 1, 2, 3, 4 are the reflections through the sides. Now, the thing is, this isn't the only copy of the dihedral group inside S4. There are two others, where instead of taking the cycle 1, 2, 3, 4, you start with the cycle 1, 3, 2, 4, or instead of starting with the cycle 1, 2, 3, 4, you start with the cycle 1, 2, 4, 3. So there are 6 4 cycles in S4, and they're divided up among these 3 subgroups, 2 in each. And also, there are different transpositions. So this one contains 1, 3, and 2, 4. This one contains 1, 2, and 3, 4. And this one contains 1, 4, and 2, 3. So the 6 transpositions are also divided up into 3 pairs. But all 3 subgroups contain all 3 of the elements which are products of transpositions, and the identity, of course. And the thing about these 3 copies of D4 is that they're conjugate to one another. But one way to think about what's going on is that if we, instead of label, so if we remember, I showed that the first one comes from labeling the vertices 1, 2, 3, 4 in that way. Suppose we just, for some inexplicable reason, decided to label the vertices differently. So there's no way to change this square into this square by a symmetry, because you have to, I mean, here 1 is next to 3 and 4, and here 1 is next to 2 and 4, and here 1 is next to 2 and 3. To change them into each other, you'd have to break them apart and reassemble them. And if you construct the dihedral group for the squares, but having labeled them in this way, you'll get the 3 examples that I gave before. So in this one, R is 1, 2, 3, 4. In this one, R is 1, 3, 2, 4, because 1 goes to 3, 3 goes to 2, 2 goes to 4, 4 goes to 1 as you go around the square. And here R is 1, 2, 4, 3. And if you work it out, you'll see that these are the 3 copies. And these 3 copies of D4, these are 3 subgroups of order 8 inside S4, they're conjugate to one another. And you can just check that if you conjugate the first one, which is the usual D4 that we look at, by the transposition 1, 2, then it takes you to this picture. And if you conjugate by 1, 4, it takes you to this picture. So in this case, there are 3 Sylow 2 subgroups inside S4, all conjugate to one another. Okay, now we can begin the proof of Sylows theorem to see that this is a general phenomenon. And we're going to take advantage of the theory of group actions acting on the set of Sylow P subgroups of the group. So let's think about some facts about what happens when you have a group and a subgroup and then another subgroup. You have a group and then you have a subgroup, and then the group acts on the subgroups by conjugation. So let me fix a typo here. So the first thing to notice is if you have a subgroup H and G, then you can consider the collection GHG inverse as G runs through G. Now, if H is normal, this is just a one-element set. But in general, as we saw even in the previous example with S4, if it's not a normal subgroup, these are going to be a group of different subgroups. And that collection of subgroups is, because we know that the conjugation is an action on the set of subgroups, this is the orbit of H under conjugation. And we know some things about this situation. Namely, that we know that the orbit is in bijection with the cosets G mod GH, where GH is the stabilizer of H under conjugation. This is a general fact about group actions. that the orbit of a point in an action is in bijection with the cosets of the stabilizer. We worked this out in our discussion of group actions. What does it mean to stabilize H? Well, it means that we're taking just the elements in G, which when you conjugate H by that element, you get H back. So if we were to go back to our S4 example, the stabilizer of one of our three subgroups would be all the elements which, when you conjugate H1, for example, by that element, you get H1 back. In this context, this subgroup, the stabilizer of a subgroup H under conjugation, has a special name, and it's called the normalizer of that subgroup. And the reason it's called the normalizer is because the stabilizer, or the normalizer in this particular case, has some properties related to the failure or success of H at being a normal subgroup. So the first thing to notice is that the normalizer is a subgroup. It's the set of G which have the property that GHG inverse is equal to G. So, and it contains H. That's the first thing, because certainly H inverse is equal to H for all H in H. But even better than that, H is a normal subgroup in N of H. So the picture here is typically you have the group G and you have a subgroup H, and the normalizer is going to be in between those two. It's going to contain H and be a subgroup of G. But even though H is not normal in G, it's normal in the normalizer of H. And why is that? Well, it comes directly from the definition. Because if G is in the normalizer of H, then by definition, GHG inverse equals H. And that's what it means for H to be a normal subgroup of normalizer of H. In some sense, normalizer of H is the biggest subgroup which contains H and for which H is a normal subgroup. And I don't think we need this result, so I'm not going to prove it. So this, I might give this as a homework problem. If you go back to the S4 example just briefly, what is the normalizer, for example, of this copy of D4? Well, any other element that you add, since this group, the index of this group is 3, any element that you add is going to be in a different coset, and you're going to get all of S4 back. So in fact, these groups are their own normalizers. So just another thing to test your what's going on here. If you take a copy of D4 in S4, which is a Sylow 2 subgroup, then the normalizer of D4 is equal to D4. And one way to see that is that we know that the conjugates of D4 are in bijection to the cosets of the stabilizer. But we know that there are 3 conjugates, which means that the normalizer of D4 has to have index 3. But D4 is inside the normalizer, and that's inside G, and this has index 3. So the only way you could fit the normalizer of D4 in between these two is if these two things are equal. Okay. Now, if P is a Sylow P subgroup, then its normalizer has some additional properties. And the first one is that the index of P in its normalizer is not divisible by P. So why is this true? Well, we know that the order of G is power of P times some number M, which is not divisible by P. And that the order of P is P to the R. That's what it means to be a Sylow P subgroup. You're as big a power of P as you can possibly be. So the index of G and P is M, not divisible by P. The normalizer of P is a subgroup of G containing P. And we know that the index multiplies in towers of subgroups in this way. We proved this way back in our Lagrange's theorem section. And so since this number is not divisible by P, neither of these numbers can be divisible by P either. So that's why this number is not divisible by P. And at the same time, if you have an element, if G is in the normalizer of P, and it's of order P, and it's of order P to the S, then G must belong to P. So in other words, the P is one way to say this is that P is a Sylow P subgroup. Well, let's not put it that way. Let's just prove this directly. And why is that true? Well, suppose you take G in N of P and you look at the quotient, N of P mod P. Since P is normal, N of P mod P makes sense, and this is a group of order, let's call it K, where P does not divide K. So if G is in the normalizer of P, then the coset GP, if G has order a power of P, then GP has order power of P. In normalizer P mod P, because, I mean, we know that GP to the P to the S is G to the P to the S P, which is P, because G to the P to the S is the identity. But the only element of prime power order in a group whose order is not divisible by P is the identity. Because we know that the order has to be a divisor both of P to the S and of K. And since P doesn't divide K, that tells you that the order of GP has to be 1, and that tells you that GP is P, and that tells you that G is in P. So whatever this group N of P mod P is, in our example from S4, it's the trivial group, but whatever group it is, all the elements of prime power order belong to P. Now we can actually use what we've got here to prove Sylows theorem, second theorem. So we have a subgroup, a Sylow P subgroup, let's call it P1 of G. And we look at its conjugates, and we assume there are K conjugates, P1 up to Pk. And now we take another Sylow P subgroup. We don't know where we got it, we just picked it. It's somewhere out there in G. And what we want to show is that this Sylow P subgroup occurs in this list somewhere. And the proof is by counting. And it's similar to what we did with, for instance, the proof of Cauchy's theorem. And the idea is the following. The first thing to notice is that K, which is the number of conjugates at P, is given by the index of the normalizer of P in G. That's our standard result on the size of the orbit. Namely, there's a bijection between the orbit and the cosets of the stabilizer. So the normalizer of P is the stabilizer of P1. I could put P is P1 here. And so the index is the number of conjugates. And we know that this index is not divisible by P. Because remember, if you look at the index, this right here is the index GP, which is M, where the order of G is P to the R, M, and the order of P is P to the R. And this is not divisible by P. The second thing is now we take any Sylow P subgroup and we let it act by conjugation on the set X. So because the set X is all the things you can get by applying arbitrary elements of G to P, and Q is a subgroup of G, if you take elements of Q and you apply them to P1, it's going to rearrange the elements in this list, but it's possible that you don't get all the elements in this list. So what happens is, so because Q is contained in G, we know that Q P1 Q inverse is Pi, where I is 1 up to K, for all Q in Q, because that's true for any element of G, and Q is in G. And so, X has a Q action. It's a set with an action by Q. Now, when you have a set with a Q action, that set is divided up into orbits for the action of Q, and each orbit is going to have this many elements. The Q so if Pi is one of the elements of our set X, then the stabilizer QPI, which is the set of G in Q, such that GPI G inverse equals Pi, this is the same thing as Q intersect normalizer of Pi, because the condition here is, on the one hand, you have to be in the normalizer Pi, and on the other hand, you have to be in Q. So those two things together give us this. And we know that the orbit is in bijection with the cosets of the stabilizer. And so we know that each orbit has this many elements. And so if we pick representatives for the different orbits, we can write K, which is the total number of elements in the set X, as a sum of the number of elements in each orbit. Standard trick for group actions. But each of these numbers is a power of P, because Q is a Sylow P subgroup, so its order is a power of P. On the other hand, K is not divisible by P. So if we look at this sum, K is the sum of these indices. If all of these numbers are powers of P, and this is not a power of P, not even divisible by P, then at least one of these numbers has to be 1. Because if they were all divisible, they're powers of P, so if they were all divisible by P, their sum would be divisible by P, and that would mean that K was divisible by P. And that didn't happen. So it follows that there is an I with the index Q intersect N of Pi equals 1. And that means that Q intersect N of Pi is equal to Q, and that means that the normalizer of that prime, of that Sylow P subgroup, contains Q. Because if you intersect Q with a set and get Q back, that means Q is entirely contained in that set. So Q stabilizes one of these PIs. But at the same time, every element of Q has order of power of P. So if Q is in the normalizer of PS, and every element of Q has order of power of P, then we prove that in that case, every element of Q is actually contained in PS. But Q is a Sylow P subgroup and PS is a Sylow P subgroup, so they have the same order. So they're equal. So what we did is we showed that if we took an arbitrary Sylow P subgroup, it has to occur on our list. So that's a proof of Sylow's second theorem. And let me just briefly state a corollary because it's right in the proof and it's a very useful fact to know in general. So if you take any subgroup of G, not necessarily a Sylow subgroup, so maybe it's like for S4, it doesn't have order 8, but it has order 4. So its order is a power of 2, but not a maximal power of 2. Then that H is contained in a Sylow P subgroup, maybe more than one. So any element in a group of order 24, any element of order 2 is contained in a subgroup of order 8. And the proof is exactly the same as we just did right up until the very end. Remember, at the very end, instead of Q, if we didn't assume it was a Sylow P subgroup, but just a subgroup, all of whose elements have prime power order, everything would go through the same, and we would end up showing that Q is in the normalizer, but every element of Q has P power order, so we would get that Q is in one of the Sylow P subgroups. But we couldn't conclude they were equal because Q might be smaller. So Sylow's second theorem really tells us that if you have an element of prime order, for example, you can always find a subgroup of prime power order as large as possible, which contains that element of prime order.